Our current autonomous path implements extensive use of drive encoders, IMU, and PID controller to accurately navigate the field. For increased consistency, we designed a program that holds to a specific heading while driving forward using the control hub's built-in IMU. Doing this allows us to be within less than 1 degree of heading error at the end of each run. The autonomous pathing that we are currently developing for our league championship uses odometry modules, which are also known as dead wheels, for greater accuracy. Odometry modules consist of a custom 3D printed holder that mounts Omni wheels onto an encoder. The module itself is unpowered and only rotates when the robot moves across the field, which allows it to track our true position as opposed to a motor encoder, which will only tell you how far the wheel is rotated and does not account for slippage or disruptions in the pathing.
As part of summer preparations, we learned the basics of Doge Commander, a command-based library to program in. Command-based programming is different from standard loop-based programming, as it runs off of asynchronous commands rather than synchronous loops. This year we implemented OpenCV through a customized grip pipeline with an external webcam to detect the number of rings at the start. This allows us to place the wobble goals in the correct drop zone every time without failure. We determine the number of rings by creating a bounding box around where the rings should be. Then we set a horizontal cutoff line for what is 4 stack or 1 stack. If we detect nothing, we assume there are 0 rings. We can also tune the specific HSV range for the color of what we detect as a ring.
Through testing, we realized that our shooter became less accurate at lower battery levels because we were running at a percentage of its max available current. When the battery level drops, so did the RPM of the wheel, which caused our shooter to be less accurate. To solve this, we added a PID to our shooter motor to control the velocity of the wheel by having it reach a target RPM. This helps with both accuracy and the time it takes to rev up to our current shooting velocity.
To assist our drivers, we created set positions in teleop through a state machine to grab and stow the wobble, and then drop and release the wobble with only 2 buttons. State machines, or more commonly called finite state machines, are simple yet powerful programming methods. Finite state machines are, in essence, a way to run any number of different actions dependent upon a state. A state can be anything from a button press to a sensor output. As mentioned, we use a finite state machine to communicate between a wobble arm and wobble gripper to pick up and put down the wobble goals.